Hey guys, Mr. Carlson here. Let's talk about ionization energy. In the previous video, we were talking about what an ion is and how ions are formed. Remember that an ion is something that has a charge, so either a positive or negative charge. And the way that we become an ion, or the way that different atoms become ions, is they either lose electrons or they gain electrons. Specifically, when we're talking about ionization energy, we're talking about when we lose electrons, because the ionization energy is defined as the energy required to remove an electron from a gaseous atom. So let's say I've got some gaseous lithium atoms that are floating around. The ionization energy for lithium then is basically the amount of energy that I need in order to get this electron away from lithium. That's what ionization energy is how much energy is required in order to remove this electron from lithium. Lithium, remember, is number 3 on the periodic table, therefore it has 1, 2, 3 electrons. And remember that lithium also is in group 1, which means it just has 1 valence electron. So to get rid of that 1 valence electron, it takes 8.64 times 10 to the negative 19 joules. That's what we measure energy in, is in joules, capital J. That's how much energy we would need to remove this electron from lithium to make it Li. Remember this from last week, Li plus, right? To make it an ion of Li plus 1, because it loses an electron. Now, to remove that first electron for any element, whether we're dealing with lithium or carbon or oxygen, to remove that first electron, that's known as the first ionization energy, because that's the first electron that you're removing from there. So for lithium, and so it's different for every element. Some it takes a lot of energy, and then for some it's not so much. Like lithium, this is actually kind of a smaller ionization energy. And the way that we want to think about ionization energies is that how strongly an atom's nucleus holds on to its valence electron. So the higher this value here, if I have a really high ionization energy, that means this nucleus here is really holding on tightly to those electrons. If I have a low ionization energy, that means the nucleus is not holding on to those valence electrons as tightly, because it's easier to remove those away, so it's not being held on as tightly. And so what we can say is that if I see something with a high ionization energy, that means that the atom has a strong hold on its electrons. And conversely, if it's got a low ionization energy, that means it does not have a very strong hold on its electrons. So something that's got a low value, I can assume is probably going to form ions very easily, or it's going to lose its electrons very easily, I should say. And if it's got a very, very high value, that means it's not going to lose its electrons very easily. So could we remove more than one electron, though? So up here with lithium, it's just got 1 valence electron. And so once we remove that 1 valence electron, it's kind of happy with that. It just needs to get rid of 1. But could we remove more than 1 if we wanted to? And the answer is yes, we could. We could remove more than 1 electron, but here's the thing. It is possible to remove more than 1 electron from an element. So let's say I remove 1 electron. That's the first ionization energy, how much energy I need there. But the energy required to remove, let's say, 2 electrons, if I wanted to remove 2 electrons from something, then I would refer to that as the second ionization energy if I want to remove another electron. If I wanted to remove a third electron, that would be referred to as the third ionization energy, and so on and so forth. So 4 electrons, that would be the fourth ionization energy, and we would keep going from there, right? Now, but with each successive electron that I remove, with each successive electron that I need to remove, I need more energy to remove each one. So the first ionization energy is going to be the lowest one. If I want to remove a second one, it's going to be even higher. If I want to remove a third one, it's going to be even higher, and so on and so forth. And so there's some patterns that we see with that. Let's first look at this pattern right here. These are for that they're showing us groups, or sorry, not groups, periods of the different periods of the periodic table. So, for example, what we've got here is atomic number along the bottom here, and along this side we've got the first ionization energy. The first ionization energy. So remember that is the energy required. The energy required to remove just that first electron. So one electron from that. Let's look at, if we look at period 1. So remember, period 1 is right here, hydrogen and helium. Those are the only two elements in period 1 here. If I look at that, moving across from hydrogen to helium, if I look at the ionization energy, notice there's a huge jump, right? So for hydrogen we see that ionization energy is much lower than helium's. And then if I go to the second period here, period 2, where we've got lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, all of these elements here in period 2, if I look at how those ionization energies look, so lithium has the smallest ionization energy. And then in general, there's a couple spots where it kind of like ticks back down, but in general, we get a big increase until we get to our noble gas, right? Neon. So as we move across, what we see is that as we move across a period, like this, the ionization energy increases. The ionization energy increases. So the ionization energy for lithium and beryllium is much smaller, but as I get towards the right-hand side of this periodic table, they get a lot higher. So these elements over here, these nonmetals and the noble gases and things, they really hold on to their electrons, but our alkali and alkaline metals over here, they kind of give up their electrons pretty easily. Low ionization energies, high ionization energies. That's kind of the pattern that we see here. And notice how it's interesting that the ones that have the highest, right, are these noble gases. Because again, and we keep talking about this, those noble gases, right, they have that full outer shell of electrons, and so they don't really need to give up or take electrons. They don't really need to bond with anything because they're so stable. They have a really good hold on those electrons, basically. And anyways, so that's what we see from that. Now, another thing. Going back to this, where we've got second and third and fourth ionization energies. If we look at that, let's come over to this table here, and let's look at the elements in period 3. So these would be the elements in period 3. So let's come back over here, period 3. So going from sodium to argon, okay, looking at just these elements here. If I look, there's an interesting, what we see here is, let's think about sodium for a second, okay, sodium. If I look, sodium's in group 1, which means it has one valence electron, right? One valence electron. And I notice that if I look at the ionization energy for the first ionization energy to remove one electron, the energy required to do that is 496 kilojoules per mole. That's just kilojoules per mole is, we'll just think about that as our unit of energy, okay? So 496 kilojoules per mole if I want to remove that first electron. But then, now remember that if we were to draw, let me move over here, if we were to draw for sodium, right? Sodium, whoops. So sodium, it's got a bunch of electrons here. So it's got these 2 electrons in its first, it's got 2, 3, 4, 5, 6, 7, 8, and then it's got an electron here, right? So if it removes that electron, okay, that first ionization energy there, let's go back to this. It's going to take 496 kilojoules of energy to pull that away from there. And once it does that, if it removes that, remember it drops back down now. This whole thing is gone because there was only one electron there, so this whole energy level is gone. In fact, let's remove it, right? This whole energy level is, oh no, it's going to, we'll just imagine that this is gone. And it's going to drop back down to this, okay? And so if I want to remove a second electron, that second electron that I'm going to remove is coming from now this shell here, which has 8 electrons on it. It's got 8 electrons, it's got a full shell now. And so to remove one from here is going to be much, much harder to remove. It's going to have a stronger pull on that. And so that's why we see, you'll notice that there's a huge jump in that second ionization energy. So the first one is only 496, not that much, but then it jumps up to 4,560 kilojoules to remove the second electron, right? Let's look at magnesium. If I take a look at magnesium, magnesium has 2 valence electrons, right? And so if I look here, the first 2 ionization energies are relatively small. It's not a huge jump to go from 738 up to 1,450. Not a huge jump. It does go up a little bit, but it doesn't make a huge jump. But then once I go to the third ionization energy, then it makes a really big jump again, right? It goes from 1,450 to 7,730. Because again, if we think about with magnesium, it's going to look a lot like, change the color to white here. For magnesium, it's going to look a lot like sodium, where it's got those 3 energy levels here. And it's got those first 2. It's got 8, 2, 3, 4, 5, 6, 7, 8 electrons. And now this one has got 2 electrons. And so it's going to be easy to get rid of those 2 valence electrons. But once I get rid of those 2, it's going to be a lot harder to start removing these inner electrons, right? And see, that pattern kind of continues. If I look at aluminum, change back to black here. If I look at aluminum, it's easy to remove those first 3, because aluminum is right here on the periodic table. It is in group 13, which means it's got 3 valence electrons, right? So group 3A, 3 valence electrons. It's easy to remove those 3 valence ones, but as soon as I remove those 3 valence electrons and I drop down to the next level with those inner core electrons, then it jumps up to a huge, I need a lot of energy to remove those. And that's the pattern we see. Silicon, which is in group 14, has 4 valence electrons, right? And so those first 4 are relatively easy to remove, but then once I get past that, those inner shell electrons are very difficult to remove, all the way until we get to, right, argon. All 8 of those valence electrons are very difficult to remove, right? And so that's the pattern that we see, is that how many valence electrons you have. So this, remember, is 5, 6, 7, 8, except for helium in this column. Remember, a lot of you guys forgot this on your quiz. Helium, even though it's in group 18, all of these guys have 8 valence electrons. Helium only has 2, because the first period here can only have 2 electrons. And so helium only has 2 valence electrons. It's our exception to that rule. But what we see is, with these ionization energies, is that, so these guys, remember, have 2 valence electrons, they have 1, is that it's easy to remove those valence electrons. So those are the ions that they typically form. But once you get past that, those inner core electrons are much more difficult to remove. Okay? All right. I think we spent enough time on that. Let's move on to the last couple things here. So the trends within periods and within groups. The general trends are this. The first ionization energies generally increase. They generally increase as you move from left to right across the period. We've kind of already talked about that. So as I move across a period, so if I move across period 2 here, moving from left to right down this period, the ionization energy will increase as I'm moving that way. So these elements over here on the right hand side have much higher ionization energies. They hold on to their electrons, but these guys over here kind of give up their electrons pretty easily. And then as I move down a group, going this way, as I move down a group, the ionization energies generally decrease. It gets easier to remove those electrons as you move down a group. So coming back to the periodic table, as I move down from lithium down to like something like cesium, it's much easier to remove electrons from things like rubidium and cesium than it is lithium. And think about it, it's because as you get to like the 4th and 5th and 6th and 7th period here, each time you go up a period, remember you're getting further and further, those electrons are getting further and further away from the nucleus. And so things like rubidium and cesium and francium, their electrons are so far away from the nucleus that it's very easy to just pull those valence electrons away from them. So the ionization energy going down a group will decrease. So ionization energy increases this way, and it decreases going down a group. So we can think about kind of like diagonally, actually. So things like fluorine right here, fluorine really holds on. It's like the one that really holds on to its electrons. But as I move this way diagonally, I get to elements that are just barely hold on to those valence electrons. They're so reactive. So that's the pattern that we want to keep in mind with those. And the very last thing here is I just want to make sure that we understand this. The octet rule, we kind of touched on this in last week's video, but I just want to make sure that we understand. The octet rule, the reason why we see all these patterns and things with ionization energies and ions forming has to do with this, and it's that atoms tend to gain, lose, or share electrons in order to acquire a full set of 8 valence electrons. Except for hydrogen and helium. Remember, whoops, oh no, what did I do? Oh no. There we go. Hydrogen and helium are the exceptions. They only need 2 electrons to have a full outer shell, but the rest of them want to have 8 electrons, and that's the reason why we see this, right? So beryllium, since it's got 2 valence electrons, will lose those 2 to drop back down to that full shell of 8 electrons, but something like oxygen, it's got 6 valence electrons, will gain 2 electrons to get 8. Fluorine will gain 1 electron in order to get from 7 to 8. Except for helium and hydrogen, those guys only need 2 electrons in order to get a full valence shell. But that's the octet rule, basically saying that most atoms want to get this full outer shell of 8, and they will either give up electrons, they'll take electrons, and sometimes they'll share electrons with each other in order so that they both have 8 valence electrons. But we'll get more into the octet rule a little later.